thank you for the invitation. It was my intention to come there in person, but there were some bureaucratic problems, so I couldn't join you there in person. But anyway, thank you. So we switch focus a bit, and we're talking about theory, especially in the context of intensity mapping, and we place ourselves in the post-reionization era. So let me see. Okay. Yes. So why is that? What is the reason to focus in this epoch of the universe? So first of all, there is a large volume, which is relatively unexplored. And I hope I will convince you that there is going to be a huge discovery potential, both in terms of astrophysics to some extent, and the structure formation processes, especially in the context of galaxy formation, of course, but also in terms of fundamental physics. And the reason that this discovery potential is huge is because the large volume and the quite different scales that are being probed by these intensity mapping observables will be able, not only in terms of scales, but also in terms of redshift span, will be able to allow to break the degeneracies between the astrophysical and cosmological parameters. And the other reason is that pushing ourselves a bit to the higher redshift regime, we are possibly closer to the linear universe, in which maybe the physics is kind of more simple to be analyzed and to be this kind of retrieved from the astrophysics. So in a way, this post-reionization universe is between redshift 6 and 0. We'll place ourselves especially at redshift 2 or so, where there are fewer observables in place, right? There is, of course, the CMB lensing, but the kernel is quite broad, so it's not very informative. There is the Lyman alpha forest. At somewhat higher redshift, there are JWST galaxies, but it's a kind of unique regime which is purely probed by galaxies, which typically focus at somewhat smaller redshift, right? Euclid is expected to give us information at redshift 2 or so. Daisy is at redshift 0.9 or so. Wiggle Z is around redshift 1. And at even lower redshift, we have, of course, galaxy clusters. So what are the key questions? I'm not going to address all of those, of course, but I want just to show you what are the main questions. First of all, the evolution of dark energy at high redshift. Then we can also focus on the free streaming of dark matter at high redshift. And typically, these free streaming dark matter models, they produce a decrease of power at small scales, at very small scales. But also we can have situations in which we have magnetic fields, which can boost the power. And of course, we also know that the large volumes will allow non-Gaussianity searches and possibly constraints of inflation. I won't talk about these things because I think they are a bit too far into the future, but we'll talk about something which is more within reach of the next, let's say, few years of, let's say, data exploitation. But also the key point that I will make is that we should learn about this MH1 M-halo relationship. It means given a dark matter halo mass, how much H1 is inside or around the halo. And this relationship is kind of sensitive to feedback, to galactic feedback. And so that's why it is going to be very important to constrain this relationship and to use it in our model building. So regarding the point 1, let me show you just an example of why the high redshift universe is promising. What you see here is the reconstruction of the dynamical dark energy model. In the upper plot, you have differences with respect to an evolution of the dark energy density with respect to the lambda case. So effectively, if you are up or above this line, you are probing a universe which is different from lambda, right? So you are discovering, to some extent, dynamical dark energy. So this is a reconstruction technique in which we see, rightly so, that at low redshift, the evolution is quite constrained, by the BAO, essentially, then kind of, geometrical measurements of distances. But at high redshift, the evolution of this is very poorly constrained, right? And the error bar increases, both in terms of WZ, which is the equation of state of the dark energy, and also in terms of dark energy contribution, okay, to the overall cosmic budget. And why is that? Well, because we have very few data points. Namely, we have just the Lyman alpha forest at redshift 2.3, but nothing else. And so this regime is very promising to be probed by intensity mapping experiments in the near future, hopefully, by scale mid or even before, and is going to constrain further the models that are being recently advocated by the DAISY collaboration as models which are kind of pushing towards a phantom regime or a quintessence, right? So I think that there is a strong scope for intensity mapping to fill the gap here, and I hope I will convince you in the rest of my talk. So the modeling of the 21 centimeter power spectrum is relatively straightforward, okay, in the sense that we are using this model here, which shows the 21 centimeter power as a function of wave number. As mu is the usual parameter described that is used to describe redshift space distortion and redshift. Here's the brightest temperature. This is the bias of the H1. This is the linear or nonlinear matter power spectrum, depends a bit on the flavor you want to give to your analysis. And this is the shot noise term. In the simplest incarnation of this model, all of these building blocks of the models, they boil down to these quantities here. And you see that all of these quantities, most of them, they carry inside them through an integral, this famous MH1 versus M halo relationship, right? And so this relationship can be learned from observations, of course. But typically what we do is we have sophisticated or kind of sophisticated hydrodynamical simulation with galaxy formation, with AGN feedback, with cosmic rays, whatever you might think of. And we try to implement this relationship inside the model, having learned it from these simulations, okay? So this comes with its own scatter. The scatter might be physical or statistical. We have to learn this. But you see that this function enters all of this. And then there are also the cosmological part. This is the mass function, and press ejector or whatever. This is the bias. You can come up with your realistic bias or not. It's up to you. But then the point that I want to make also is that we are not totally free here, right? The omega H1 is very much constrained by Damplerman alpha system observations, which are very independent from intensity mapping. They are typically done by absorption lines. They come with their own statistical error. The bias of H1, again, is something that you can also measure from the data, right? And indeed, there have been alpha survey has measured the bias of H1, even though at redshift 0, or kind of local redshift, not at very high redshift. But to some extent, all of these quantities that you have here, they're not totally free, right? You can put informative priors and then, marginalize over some nuisances on these parameters. So how would the H1 distribution would look like at a redshift 3 around 10 to the 13 halo? It would look like something like this. This is a simulation by TNG Illustris people, Villascusa Navarro Italy. Here you have the gas distribution, is the column density projected with a given slice. And here's the H1. You see they're quite diverse to some extent. So it's kind of expected that if you pierce along this yellowish region, you will end up having a Damplerman alpha system. But you see that, it's the fine structure of this H1 distribution is very, very kind of cosmic web-like, right? You have really filaments, you have lumps of cold gas, you have regions in which there is not H1, possibly because there is less gas or possibly because the gas is very hot, right? And so you want to learn as much as you could from these high redshift simulations at very high resolution. Unfortunately, this plot here is not directly observable, but what we do observe is galaxies, right? What we do observe maybe at high redshift in small fields, but we can learn from this. And so we can ask somehow to our simulation to bring us closer to the observations. And so what you see here is the MH1 versus M halo relationship, in which we divide the contribution of central galaxies and satellite galaxies. And we also explore the redshift evolution of this. So this color coding here in this plot, this arrow goes from redshift 0 at the bottom up to redshift 5. And so here you see that for small mass halos, well, relative small mass 10 to the 11, the contribution of central galaxies is much more dominant. But as soon as you start moving to large halos, right, 10 to the 14 or so, then the contribution of the satellite starts to be also more important to some extent than these central galaxies. And these models, they have feedback, of course, and these are kind of calibrated against low redshift 0 observations and extrapolate through a semi-analytical galaxy formation model, which in this case is called Gaia, to high redshift, right? So there is a bit of extrapolation, there is a bit of freedom, but for example, you want to reproduce the luminosity functions, stellar mass densities in galaxies and things like that. So again, there is not complete freedom. But this helps us a bit because it's going to bring something informative in our framework. And for example, the idea is you can use higher order statistics. You can cross-correlate, for example, the H1 brightness temperature with bright galaxies, with, let's say, not so bright galaxies, with red galaxies, with blue galaxies, star-forming galaxies, and things like that. So you can come up with techniques that will enhance possibly the signal to noise compared to a simple power spectrum analysis, which may be likely to be hampered by foreground removal, systematics, and wedge effects. And this is something we're working on also with Suman and Leon there in India. So this is galaxies, but if we are inside galaxies, then you might wonder how is the H1 is distributed. So the same plots that I showed before, now we can kind of extract some H1 profile around many 10 to the 13 halos. And you see that the scatter is huge, right? It's really large. And the scatter is most likely physical. It's due to the fact that the halos, there could be environmental effects, there could be feedback different, there could be different merging histories of these halos. So it's quite intriguing that if you want to capture all this scatter, maybe you should marginalize over these quantities, right? There are not small scales, but nevertheless there are some halo-inspired models which are sensitive to even how you distribute the H1 inside the halos, right? So the model of H1 halo is important, also in the context of halo models, which are analytical to some extent. The large scatter in the H1 density profile is also informative, but the rationale behind is that by looking at these quantities, in principle, we could be sensitive, of course, to dark matter nature and fancy things like that. But in practice, we're really characterizing the amount of cold gas at our disposal at high redshift, which we know is the building block of star formation, which will be the reservoir giving rise to star formation at somewhat maybe lower redshift at the cosmic noon, let's say at redshift 1, okay? So now we have to model this, especially in the context of SK1 mid, I would say. And so what you see here in the left panel is the modeling of the monopole of the power spectrum in 21 centimeter brightness temperature and the quadrupole, with possibly realistic error bars, right? We try to be as close as possible to the instrument. And so what you see here is the power spectrum is damped at small scales. What is causing this damping is the beam, right? The beam is killing, suppressing somewhat small and medium scales. And this is very important, right? Because maybe this is telling you, look, you don't need a very high degree of sophistication in modeling how the H1 is distributed inside each halo, because the beam will kill this information. But nevertheless, look at the error bar here in the mildly nonlinear regime. It's very, very small. You see also the BAO, you see these things are the BAO. So nevertheless, even if you have the effect of the beam, right, kills information, but the scales, they come with a very small error bar, the power spectra measurements or correlation function. And so then you can learn quite a bit. And, you know, in this framework here, somewhat the small redshift beams are only affected by nonlinearities. And for the other power spectra, linear theory is kind of enough. So compared to Planck-only data, we have an improvement of a factor 4 on the error of H0 and omega cold dark matter, right? Why is that? Well, the reason being that you measure the shape of the power spectrum. Of course, you measure also the amplitude, but we are kind of conservative in setting the amplitude right. We allow freedom to bracket all the uncertainties. So when I refer to nuisances, I refer really to this fact that we let kind of freedom in the amplitude of the power spectrum, which should bracket our uncertainties in a very conservative way on the bias of H1, on the brightness temperature even, and all the things that are captured by an overall shift of this, which could also have in our framework a little bit of redshift dependence. And so the bottom line is that nevertheless, this fine binning in redshift will allow you to measure the shape of the power spectrum. And once it is combined with Planck, you improve a lot over these two quantities. We know how this could be important, right? In terms of H0 tension, but also in terms of models in which you have different values of omega matter. Indeed, let me tell you that this dark energy evolution, dynamical dark energy evidence from DAISY data is really coming by a mismatch from the omega matter, thereby omega cold dark matter, measured from CMB and the one measured from the BAO in galaxies, okay? So this will be really a new thing in a way if you can measure this independently of galaxies, which of course are much more precise. So when you talk about autocorrelation, people, they look at you like as if you are crazy, in the sense that we know that it's very difficult to measure. Nevertheless, we can say, let's try to do things in cross-correlation then. Maybe in cross-correlation, we already have data now that we are using. Cross-correlation, the signal could also be extracted. And the answer is yes. So we modeled the cross-correlation. In this case, we have two data sets that are fake, mock, but DAISY and Euclid. And we model very simply like this. We cross-correlate with the spectroscopic samples. They have to have kind of large volume, always in the context of SK1 mid. We also allow for nuisances. And the bottom line is that at the end, if you can get constraints that are similar to the autocorrelation, right? For the autocorrelation, for example, the measurement of H naught could be of 0.25% in terms of H naught. Once you add to this autocorrelation, this cross-correlation information is of the order of 0.33%. But you can also, for example, say, okay, I don't trust my autocorrelation, and then the constraint will be weaker by a factor of 2.5 or so. I work just with cross-correlation of 21 centimeter intensity with galaxies, and I have a constraint of the order of 1%, okay? Again, this is not maybe as competitive as we would like to with respect to galaxies, but is on the verge of being competitive, but is kind of exploring somewhat different regime. The other thing that I want to show you is that you can also do baryonic acoustic oscillations. Of course, when we started working on this, we said it's going to be very difficult, right? Because the angular resolution is so poor that the correlation function of your 21 centimeter observable will be totally swamped. And this is the case, right? So what you see here, the black line is the correlation function with a clear BAO peak. If you smooth it at 25 megaparsec, you get this line here, so no peak whatsoever. But what we didn't appreciate, and we appreciate soon after, right, is that if you instead do things as a radial BAO, which is likely to measure Hubble distances rather than angular distances, things are very, very clear because in terms of frequency resolution, we know that the Testimac experiments are going to be exquisite, right? And so what you see here is the ratio of the power spectrum 1D with the no wiggle power spectrum, and we see that the wiggles are very, very prominent. There is a but here, there is a problem, right? There is in the sense that we know that the amplitude of the 1D power spectrum is going to be smaller than 3D by a factor 1 over R squared. So the amplitude gets smaller, fine, but still the wiggles are present. Here the amplitude will be large, but we don't see any wiggles, and we cannot do any geometrical reconstruction of distances in given beams, right, in this case. And so together with David Alonso and Paco Villascusa Navarro, right, a few years ago, we tried to be, of course, as close as possible to the experiment. And we had the cosmological signal, we had the mask, we had foregrounds, and we removed foregrounds with PCA in a very simple way at that time. Now there are more sophisticated techniques. And we put the foreground mask, and we tried to extract this information. And the results seem very interesting. For example, here you see the 1D simulated, right, SKL mid at redshift 1.6. These are simulated observations, and this is no wiggle power spectrum. And you see that the wiggles, of course, are a better fit to the actual mock data. And the point is that we claim that at redshift, let's say 1.6, we can constrain, once you include noise and foreground, the BAO position at 2% level. Okay, and this is, of course, very, very interesting. I think that very few galaxy surveys are likely to achieve such a precision at such a high redshift. We can go to even high redshift 2.5, and of course we degrade a bit the resolution, the precision, the fact that beam, of course, gets larger at high redshift, and of course this kind of deletes information. And so, but in a way, the point that I want to bring here that the 21 centimeter intensity mapping can be used for growth, but can be also used for BAO. And also, we wanted to be somewhat, technical in a way, and provide also a method to reconstruct the BAO. You know that with galaxies, it's quite crucial to reconstruct, to undo nonlinearities, to sharpen the BAO peak, and to make the detection of the position of the peak very, very clear. And we did the same thing with pixels. And the funny thing is that with pixel, it works even better because it's simpler, because all these these techniques to undo nonlinearities, they're based on the Zeldovich approximation, and they are required to estimate the density on a grid. And here with 21 centimeter testing mapping, the grids come for free to some extent because it's the pixels. So the algorithm of reconstruction is even faster. And with Andrea Obulian, we looked into this, and we had halo maps. These are called halo maps, but effectively, since the halos are carrying the 21 centimeter intensity, these are effectively like looking at our mock observable, right? And here we have the difference between the position of the peak in percentage with and without reconstruction. Sigma is the smoothing of the beam, if you wish. And again, you see here that with the reconstruction, the recovery of, let's say, of the correct position is better, okay, which is one, right? We are doing this on mock, so we recover, there is no bias, and the error bar is even a bit smaller. So this will bring us another 40% improvement on the position of the peak, which of course will propagate to the final constraints on alpha and the final constraints on cosmology. And so we were so excited back then, a few years ago, that we also started to scale up experiments like IRAX, right? As we said, we call an experiment extended IRAX with more antennas. The specifications are in this paper here. And we also mocked the 21 centimeter power spectrum. We were considering also the fact that there is a wedge. We were working in an interferometric way. We had the beam, the noise, the shot noise of the tracer. We were looking at things in redshift space, of course. And so here what you see, two theoretical models in which the amount of H1 is hosted by halos above 10 to the 10 or 10 to the 11, 2 times 10 to the 10 to the 11, redshift 4. So we are pushing it the high redshift. And we ask ourselves, what is a kind of such of an observation doing in terms of dynamics and geometry? And it's doing extremely well. It's doing extremely well because, for example, it can retrieve the growth at the sub% level, and also in terms of Hubble distances that by geometry we are at the sub% level, and we consider the wedge reconstruction within the wedge, no wedge at all, and so you see how these curves could improve, and you can look at this paper. In this case, we are also putting some priors on BH1 and omega H1 at the 5% level, which I think is reasonable. But of course, you can play with this prior. This was done with Fisher matrix analysis. And another thing that we looked at was at the constraints on neutrino masses. At that time, we also considered a model in which W was varying. We were not, of course, aware of these dark energy models here. And we were exploiting the degeneracies between, let's say, Euclid and Planck observation, which have a degeneracy like this one, with against, what a 21 centimeter intensity mapping observation could bring, which is a different degeneracy line. Hence, once you combine the two, you can get very tight constraints or reasonably tight constraints in W total neutrino mass plane, right? So this was done with Fisher matrix, somewhat not so much reliable to some extent. That's why we wanted to look a bit, to scrutinize a bit better this neutrino free streaming effect. And what you see here on the left side is a theory prediction, the linear power spectrum suppression induced by neutrino free streaming, once the total mass of the neutrino is raised from 0.14 electron volt to 1.4 electron volt. Here are the large scales, these are the small scales, and you see that at the smallest mass, 0.14 in this case, the suppression is of the order of 5%, 7%, which is something for sure within reach of Euclid and even DAISY. Okay, so this will be, they really think they will measure this. So how is this free streaming neutrinos propagating on the multiple of our observables, monopole and quadrupole of the 21 centimeter brightness temperature? Power spectrum is, so in this case, it's the multiple of the power spectrum as a function of K. And so you see here that you have the two observation, mock observation redshift 0.25 and 2.7. And you see the neutrino free streaming, this is the envelope of neutrino free streaming models. And you see, of course, that most of the action is happening at the smallest scales where the beam is killing our observation, but still at somewhat intermediate scales, there are, possibilities. There is the possibility to constrain the neutrino free streaming using 21 centimeter observations. And again, hopefully these error bars that we put here are really realistic, are kind of SKA1 mid designed to be in this way. So what you see here is that another reason for why, right, this 21 centimeter is bringing us extra information in the context, in this case, of cross correlation. So what you see in this plot is H naught versus total neutrino mass. And the blue line is basically this line, this color here is flat line is cross correlation 21 centimeter and galaxies modeled in the following very simple way up here. Having marginalized over all these quantities that you see here, more specifically the bias, the brightness temperature. While this line here is the line provided by Planck, which is a very different physics, right? Here you're really probing the effect of the neutrino effect at the CMB, right? On the peaks of the CMB towards by modifying the gravitational potential. Once you combine the two, you really improve a lot. you really improve a lot in such a way that we claim that if the neutrino mass is 0.1 electron volt, by combining galaxies, the cross correlation of 21 centimeter and galaxies, Euclid and Euclid with Planck, you can get a 3 sigma detection. Even though if you add the nuisances in the fully conservative way, this detection is washed away, okay? But we are not surprised by this, right? Even people like doing CMB plus DAISY galaxy cluster, which is much more precise than this, they don't get any detection yet. Maybe they will at some point, but I think that the neutrino field is moving in such a way that if you want the detection of neutrino free streaming, you are very likely, in order to achieve that, to combine more than 2 observables, right? With different redshift, with different systematics, with different statistical errors. So, but what about current data? We do have this wonderful exercise, right, with wonderful observation, Meerkat cross-correlated with Wiggle Z, Cunnington et al., 7.7 sigma detection of cross-correlation. And we said, maybe we can look at this data too and see what we can get. Let me tell that we know already that in the context, let's say, of simple halo models, like very simple, in which you distribute H1 inside halos, the quantity that is actually constrained is basically a combination of omega H1 times the bias H1 times this R coefficient. Okay, so we know that you cannot really do cosmology at this very time, but maybe we will soon, right? And so what we get is something like this. So here we had Meerkat plus Wiggle Z real data, in this case, plus the nuisances, right? And so these are not CMB, not whatsoever, maybe just a tiny prior omega baryon, but does not impact. And what you see here is the posterior in the H0 omega Coldar matter plane, with and without the nuisances, right? You see these degeneracy lines that was something we expected. Switching on and off the degeneracy shift the contour by an amount which makes a bit not very comfortable. We think we know the reason for this. But suppose we would like to use the most conservative contour, which is this one here, we get not even a 2 sigma detection of omega cold out of real data in a very conservative way, right? Without using basically any prior. And I think this is remarkable, right? The first measurement, one among the first measurements of omega matter at high redshift, well, right redshift, not so high in this case, using a completely independent data set in cross correlation, not using the CMB, not using galaxies, not using BAO. And I think it's very exciting because I think it's likely that with larger volumes, better understanding of systematics, these numbers will clearly improve on a very short time scale, hopefully, right? So let me finish. So I think the post-reionization universe is a very interesting place to test structure formation and galaxy formation theories. And intensity mapping will be sensitive to H1 distribution, of course, especially this mass distribution. However, at poor angular resolution, we know this. That's one of the advantages of intensity mapping. I showed you that a promising way to constrain geometrical information in the universe is to use the 1D radial BAO. We did some work in this extent, also looking at the reconstruction with pixel, which is a new technique, very simple though. And the power spectrum will constrain the growth, and so the BAO will constrain the geometry, and thereby I think there is a sweet spot for this community to really have an impact, right? And do something quantitative in terms of constraining theories, like these dark energy theories, or constraining the neutrino mass, which we know should be there, right? The neutrino free streaming. And so this is likely to be done, at least for the for some years in cross correlation. But again, it's fine. We will learn a lot also about galaxies, the galaxy bias. We can try to be clever, right? To build up new estimators, to kind of get a bit of synergy with the machine learning community, not only to remove foregrounds, but also to come up with new kind of ways of retrieving most of the information. And if you're interested in astrophysics, as I think most of you are also interested in, then the MH1 versus M relationship is also could be also constrained by these observations. And you can learn a lot about how H1 is distributed inside and outside halos. Thank you for your attention. Thank you.
Questions?
Hi, Matteo. So I have a question regarding this one radial BAO.
Yes.
So you showed the forecasts or promises with high racks. So I was wondering what would be such a thing for SKA?
Yes, for SKA it will be a bit. Yeah, I don't come up. I should look a bit better at the paper, of course. There we focused on two. Sorry, we focused on some scaling up of instruments which are called extended chime, extended IRAX, and IZ fast, which should be something like a scaled up instrument, which sorry, a scaled up radio telescope, which I don't recall now at the moment. So for SKA, I don't have numbers, but should be worse than this, right? It should be worse because here we want a little bit of interferometry too, right? And maybe we could use SKA as in, which SKA will be good, but yeah, I don't recall the numbers. Typically, they should be similar to these ones, to the orders of sub% measurement of h of z at high redshift. The SKA estimate is this one here. With this, sorry, this one is made really, in the Boolean paper was made with Fisher matrix. In this case, is made for SKA mid. So to answer your question, sorry, I have the answer is h of z will be measured sub% level at redshift 2.5. Yes, sorry, yeah, I have this.
Thanks.
This is regarding the neutrino mass, sum of neutrino mass. If you do not put any prior on that, DAISY still shows that it peaks at negative value, right? Yes. Including 21 centimeter, do you think like you get a positive neutrino mass or like what's going on there?
Okay, so why is that DAISY is pushing us to have negative neutrino masses? The reason is very simple. The reason is that the omega matter of the CMB is larger than the omega matter than the BAO wants. And neutrino would like exactly the opposite. Why? Because neutrinos at the CMB are radiation, and now at least one of them is matter. So the omega in the neutrino massive universe, the omega matter of the CMB has to be smaller than the omega matter of BAO. The opposite is true from the data. That's why the neutrino models are pushed towards the negative side. Okay. So to answer your question, the present data in cross correlation of Wiggle Z do not constrain omega matter. The error bars is far too large to say anything meaningful. But still, what I think is important is to fill the gap. These are the DAISY measurements, right? To fill the gap in this region here, right? So what you see here is angular diameter distance, which is this one, and Hubble distance as a function of ratio, real data, and this is W0, WA, but the similar plot will be true with neutrinos. And so if you fill this gap here, you will constrain this model even further. So to answer your question, I believe that we need to constrain the high redshift evolution of this model. This W0, WA, indeed, when plugged in, accommodates positive neutrino mass. That's one of the reasons they like it, right? If you let this crazy model of quintessence model being phantom and play a role in the game, then all of a sudden, for free, you get positive neutrino mass. I believe that future intensity mapping observation could have a word in saying whether this at redshift 1 or so, this is true or not. Yeah. But for the moment, they don't say anything, unfortunately.
Is there any other question? Maybe the last one, short one. Okay, I don't see any other hands. Let's thank Matteo again.
Thank you all. Thank you.